Hello. So today we'll see a very beautiful problem on linear algebra. So this problem basically relate to the geometry. So to prove this theorem, we will take help of the geometry of plane, or you can say the geometry of space. But let me state the first read the problem here that it tells us that if we have a vector space V of dimension 2 over an infinite field F, then B has infinitely many subspace. So now here important to note that we have to understand what do we mean by dimension and infinite field. So dimension of V2 mean V, a basis of V contain two elements, and F is infinite field mean F contain infinitely many elements. Now to start the solution of this problem, so we'll take a motivation from the geometry of R2. So just this is you can think we will take a motivation how to start to solve this problem. So let's say we consider the plane R2, and we know R2 is a vector space under usual addition and scalar multiplication. So y and y test. We can consider the vector space R2 and now take the basis. Here we are taking the standard basis. You can say beta equals to the E1 basis. So this is nothing but 1 comma 0, and E2. So that is nothing but 0 comma 1. So this is the standard basis for R2. So this means here you can say this is E1 and this is E2. Now, for R2, it is clear that all the line passing through origin are the subspace of R2 of dimension 1. And it is clear that there are infinitely many lines passing through origin. So R2 has infinitely many subspace. But for the arbitrary vector space, we have no concept. What I meaning no concept of line, that so actually we'll write down the concept of line in V, but so the way we want to write the concept of line, so that it's come from this basically R2. So let's write how there are infinitely many one-dimensional subspace of R2. Basically, if we take a line here, so passing through origin, let's say this line if we take, so then you know so for this line, so clearly if we draw here the line passing through E1 and parallel to the y-axis, so then this will intersect the given line, so at a point, let's say here, and if we draw also here, so the vector, so you can say from here to here, this is the vector, so it is nothing but the vector is E1 plus E2. Now this vector E1 plus E2 actually span this line. So this means any points on this line is the scalar multiple of the vector E1 plus E2. All right. So now, so let's take another line. So for example, if we take here this line. So now see here, basically this line actually, the line passing through E1 parallel to y-axis intersect this line at this point. Now if we draw here a perpendicular on the y-axis, so we'll get a point here. So now this point from origin to here, it will be some multiple of E2. Say suppose that it is double of E2, so E2 of E2. So now this vector will be basically E1 plus 2 of E2. So now we take one more line here for understanding that we take here a line. So basically this line and this way. So now if we take this one, so then, let's say this is the half. So this is half of E2. So now this vector will be basically, this vector is basically E1 plus half of E2. So it is clear that if we take any line, if L is any line passing through origin, then there exists alpha, a real number, such that this line can be written as the, so this line is spanned by the vector basically e1 plus alpha of e2. So right, so this is so we, for our convenience, so this is, so yeah, right. So for every line we have find out a alpha such that the line will be generated by e1 plus alpha of e2. So it is clear that if in arbitrary vector space, so now this concept we will shift to arbitrary vector space. So how we do this? So basically, so suppose, so this is the solution of the original problem. So now let beta is a basis. Let's say I'm considering u1. Let put it here a vector sign u2. This is a basis of v. Now see, if for R2 we had basis E1, E2, and using those bases we construct the line how E1 plus alpha E2 span by this vector. So same thing we do here. So let we choose a scalar alpha from F. So define a you can say L alpha. So this is nothing but the span by the vector u1 vector plus alpha of u2 vector. So this is a, you know what we know, this is scalar multiple lambda of u1 vector plus alpha of u2 vector, such that lambda from the field F. So this is by definition. So clearly then it is a subspace, L alpha is a subspace of V, and of course dimension of L alpha is 1, although we not need the dimension, but it is necessary to know that L alpha is a subspace of V, and it is clearly subspace because we know any vector always span, if we consider all multiple scalar multiple of a vector, then it will give you a subspace. So now the next target, I'm going to the next page. We will check all L alphas are distinct for different value, for different value of alpha. So yeah, this is our target now. So how to do? So we can do many different ways. Suppose we can assume, suppose that if possible let that L alpha 1 equals to L alpha 2 for some alpha 1, alpha 2 from the field F. So what we are getting? We are getting span by u1 vector plus alpha 1 of u2 vector. This is equals to span by u1 vector plus alpha 2 of u2 vector. So now now we know that the vector u1 vector plus alpha 1 of u2 vector is in the set span of u1 vector plus alpha 1 of u2 vector. Why? Because this vector u1 plus alpha 1 of u2 vector we can write as that 1 plus 1 into u1 vector plus alpha 1 into u2 vector. So therefore it is in this span. Now you can take this is 1. So this, since these two sets are equal and these elements in the first set, so by 1, we get that u1 vector plus alpha 1 of u2 vector is in the span of this set, u1 vector plus alpha 2 of u2 vector. So now let me go to the next page. So here we can find, so then, so since this vector is in this spanning set, so u1 vector plus alpha 1 of u2 vector, this is nothing but lambda into u1 vector plus alpha 2 of u2 vector for some lambda in the field F. So now we go to the next page. So basically what we get here, now we had u1 vector plus alpha 1 of u2 vector. This is nothing but this is lambda of u1 vector plus lambda of alpha 2 of u2 vector. Just we use here the distributive of scalar over the vector under, you can say the multiplication is distributive over addition. So now we will take all the quantity to the left hand side. So then what we get, 1 minus, so 1, and actually factor the scalar out. So then 1 minus lambda of u1 vector plus alpha 1 minus lambda of alpha 2 of u2 vector. This is basically 0 vector. Now from here it is clear that 1 minus lambda equal to 0 and alpha 1 minus lambda of alpha 2 equal to 0. Why? Because this is linearly independent, because it is a basis, is linearly, since it is linearly independent, so the scalar are 0. So now these two, so what we get, we will get lambda equals to 1 and alpha 1 equal to lambda of alpha 2. So what we are getting? We are getting that alpha 1 equal to 1 into alpha 2. So this means alpha 1 equal to alpha 2. So this analysis tell us that, so we get here basically that if L of alpha 1 equal to L of alpha 2, then alpha 1 equals to alpha 2. So we can say that if alpha 1 not equal to alpha 2, then L of alpha 1 not equal to L of alpha 2. So this means, so we are getting that you can write that all alpha L alphas are distinct, where alpha belongs to F. So remember, L alpha is the line that is defined this way. So L alpha is spanned by this vector. Now now since F has infinitely many elements, so number of, so the number of L alphas are infinite. So what we are getting, V has infinitely many subspace of dimension 1. So basically here we done the theorem, this problem proofs here basically. Now we can generalize this. So I'll give you as a I'll give you this problem to think you guys. So here, so if dimension of V equals to n over a field F with number of element is infinite, and r less than n, let's say it is greater equal to 1, then V has infinitely many subspace of dimension r. So just you will try this. So I can give you the hint that just do for dimension 3, consider a space of dimension 3. For example, you can take R3, then on R3 you can find out that there are infinitely many subspace of dimension 1 and 2 the similar way, because you have the geometry. From that geometry, try to write using the algebra and all these things. So okay, so basically the idea, you have to go to your R3 and R2. From there you have lots of geometry. Just write down those geometry using vector addition, scalar multiplication, and shift that concept to arbitrary vector space, of course finite dimensional. Okay, so try this problem, the last one. It's a very nice problem. So thank you, good night.